Okay. Thank you. I am really, really happy and honored to be here today, and really glad to see all of you here. And a bit sorry for making you all wait a bit. Um, so, before we start into all these technical terms, why quantum, what quantum, quantum at IBM, and all, just let me ask you all one question. How many of you know what quantum computing is? Perhaps everyone has heard about it. How many of you know what it is, or any idea what it is? Yes. Right, right. Yes, great. Okay, before we go into this, let me just ask a very simple question. Many of you are from computer science department, I guess. You all know about sorting, right? We all know how to do sorting. Let's ask a question that forget about all what we have learned, all different kinds of sorts, algorithms, complexity. If I give you some papers, say your exam papers, and ask you to sort them by roll number, what will you do? We won't use anything like merge sort or anything. That would really look stupid. I mean, if we just say, okay, here we divide it, now we have pointers, we are moving things, this would look really stupid, right? What we do simply is we take the roll number. Okay, this is the roll number, this will go here. Maybe this is the roll number, this goes up above, this goes below, like this. That is insertion sort, right? What we do is insertion sort. What we came up with when researchers were doing studies and all these mathematical analysis, we came up with other methods like this quick sort, merge sort, and things that makes things faster. Now let's think in a bit different way. If I had all the power of nature, can I do sorting in a different manner? If whatever nature can do, let's say I can do whatever nature can do. Can you think of, just think out of the box? That's what we say here, right? Think out of the box. Can we do something different? Instead of taking pointers, finding pivot elements, or all of those things, how about, yeah, this is not very easy to think right now. How about we create an inclined plane? We put everything together, everything in the top, release them, gravity will take care of everything, right? Think of it. Just create an inclined plane, something like this, put everything on top, release them, gravity will take care of sorting. So the way nature computes, in some sense, is quite different from the way we think of computation or we do computation. Because when we came up with, say, insertion sort is the most natural thing that comes to us. But when we came up with better solutions like this merge sort or quick sort and other things, we were thinking of the way we do computation. Nature doesn't do computation like that. Nature is not restricted to a Turing machine. Nature can do a lot of things. And there are many other ways that people are thinking. Quantum computing is one of those ways by which we can do computation in a different way. And in certain cases, they are much more useful. So let's see, let's go into this. Why quantum? He was already saying why quantum. So how it all started is, this is, so my supervisor from ISI, she was from MIT. And whenever she starts her talks, she would just say that when Feynman told this thing in a conference at MIT, she was present there as a student. Shushmita Shurkole. Yeah. So she was present there, and I think I am most jealous of her for this reason. Maybe not for anything else, but I am really jealous that she was present there listening to Feynman talk about quantum computing for the first time. And this is what exactly Feynman said, that we do all this analysis. What are computers good for? Okay, when we think of computers, we say, okay, we browse internets, we do Facebook, WhatsApp, what else? We play games, we see movies, and sometimes we Google, and nowadays we use ChatGPT to do our homework, right? So, uh, but what is a computer good for? A computer is good for two things. It can do mathematical calculations, basic mathematical calculations, and it can store. It has a memory, it can store. It can do this calculation super fast. Even not talking about quantum computer or anything, even a normal computer that we have here right now, what I have here, maybe many of you are carrying a laptop, they can do it super fast. But you all know about these things, like if we are going to do some useful calculation, what sort of things? Let's say that I want to find out the ground state of some molecule, ground state energy of some molecule. Let's say I want to do some calculation or some analysis of DNAs, try to find out medicines and alls. The amount of computation, the amount of possibilities that come in there, that's like huge, that's exponential in the number of sequence or whatever, like in genes you have this AB, ACD and things like this, and all of these things, they grow exponentially, and we can, even with the best computers today, we can hardly scratch the surface of what we want to do in reality. I heard a very interesting thing, in ISI from a faculty who came from Bangladesh. He was in Buet, Bangladesh University of Engineering and Technology, and he was doing some machine learning work with mitochondria, and he was doing like he was trying to use machine learning to try to find whether for a particular disease that we are seeing, whether the mitochondria is responsible for that or not. This is the all answer that he was trying to get. That's all, nothing very specific, and there is nothing quantum about it. What he was saying is that when say a atom, a molecule, a cell enters a mitochondria and it leaves the mitochondria, the amount of processing that goes inside is so huge that even with the best computers that we have today, we cannot really simulate that. So that's just one thing that we are talking about. And he was telling us this, that I am sure every one of you have seen this, that maybe we have some symptoms of illness, we go to the doctor, they give us some medicine, it works for someone, it doesn't work for someone. Why does it happen? Is the doctor bad? No. Is the medicine wrong? No. Because when think of this mitochondria example, that the entire computation is so hard, we are unable to actually process it properly. So we will do some modeling of it, some approximate modeling of it. That's what we do. Some approximate modeling of it, and the approximation that goes in there, that is actually responsible for us not getting the entire scenario, and therefore we don't know that when we see two people with the same symptom, maybe we don't know why this medicine worked for this person, didn't work for that person. If we could get the entire process there, no approximation, we could have said that, okay, this is the reason it is not working for person B, it is working for person A. So that's kind of what Feynman meant, that all the analysis that we are doing in classical theory, I am not happy with it, because nature is quantum mechanical. If you want to simulate nature, if you want to simulate chemical systems, physical system, biological system, you need to make it quantum mechanical in some sense. And then he came up with this nice paper called Simulating Physics with Computers, where for the first time he coined something called quantum computer. He didn't know what a quantum computer is. He didn't define precisely what a quantum computer is. He just said that, okay, can we think of a new type of computer which we can call a quantum computer that will be able to take advantage of things we can see in quantum regime, but not in the classical regime that we are seeing at this moment. So this all started, and then there are like people, I would say, IBM is actually one of the forefront leaders, Charles Bennett, who is one of the beginners of quantum computing, he kind of told us this. I heard from him once that when he started working on this quantum information processing, people were like, "What are you doing? Like, I mean, doesn't make sense. Why are you wasting time? Why don't you do some work that actually makes sense?" So he used to tell me that I used to go do my own work in the daytime. At the evening, I would do my own calculations for quantum information science, because nobody was serious about it. They thought that you are just wasting your time. And there were other people like this, Charles Bennett, then there is Peter Shor, and other people like this who kind of started this, and they met in a conference and they would talk about this in the conference, and that's how things got started. And today we have classical computers, great computers, like let's say this laptop, or we have GPUs, we have clusters, and we have many TPUs and everything. But there are certain problems that we can address today, and there are still a lot of problems that we cannot address adequately, because even the best supercomputer is not up to the mark for that. So that's kind of the hope here, is that if we can simulate the nature, or emulate the nature the way it is, using properties of quantum mechanics, maybe we can solve some of the problems, definitely not all of them, or yeah, I mean, we can come up with problems that a computer cannot solve. So we can hope to solve using a quantum computer. And when we say quantum computer, nobody, at least in this moment, we envision that someday instead of carrying this laptop, I'll carry a quantum computer with me in my bag. That's not what we envision. A quantum computer will go hand to hand with classical computer. There are things a quantum computer can do better than classical. There are things that it cannot. For example, sorting. I started with sorting. A quantum, it will be like a stupid thing to say that, okay, I have a quantum computer that can do sorting. No, we can do sorting very well. There are many problems that we can do very well. No point of using a quantum computer for that. But there are problems where quantum computer, theoretically, there are proofs that it can outperform even the best classical computer. So what we hope is that together with quantum computer and classical computer, we can address problems that we are not able to address now. It's never too bad to think big. What are the things that we hope we can address in a bigger scale? Maybe finding good fertilizers, maybe getting better catalysts, maybe this kind of new drug discovery. That's the example I was talking about before. Or even predicting the better financial models and things like this. Yes, of course, we are thinking pretty big, and there is no harm in thinking big. Like, why not? Even before anyone asks, like, there are people who are still skeptic, and they ask that, okay, are we there? But the answer that I prefer to say is that there is no reason we cannot be there. Maybe not today, but in a few years, hopefully. So, having said all of these, let's take a jump down and see what is quantum. It's like when I was a master student in Calcutta University, we had our first class in VLSI, and the faculty came and say, oh, you know, Intel Core i5, and this is what we will learn. And we were very excited. Okay, we are going to learn about Intel Core i5 here. And then after saying all of this, he said that, okay, we will start with what is a transistor. So, and that's something what I have said, all of those things that we can do, nitrogen fixation and this, but let's understand like what is quantum, because perhaps many of you have not taken a classes there in quantum computing. So if we think down, we all know about this, that we do algorithms, we do all of those stuffs, but in the end, if we look down in the classical system, there are some logic gates that occurs, right? And it processes zeros and ones, and this logic gates can be AND or NOT, XOR or something. We call these gates. Similarly, when we think of a quantum circuit, there are a few things. So we start with classical bits, which are zeros and ones. We start with quantum bits, which are called qubits, and they are just written like that funny thing, that bracket thing there. It's called a Kate notation, but don't worry about it for this, at least that's a mathematical notation. We don't need to worry about this. Just think of that bracket there is kind of distinguishing that it's not a quantum, it's not a classical bit, it's a quantum bit or a qubit in general. Then we have this H things written, they are like quantum gates. Just like we have AND gates, OR gates in classical, they are quantum gates. This H gate is particularly called Hadamard gate. What we don't think, very particularly for classical systems, we say that, okay, we have classical bits, we have done these gate operations and we get the output. We don't really think that we need to measure the output, because yeah, I mean, whatever it is, we will measure and we will get it. But when it comes to quantum, we really need to think of measurement, and we will see why. So in classical, we usually think of two things. First is the bits, and next are the classical gates. In quantum, we will think of three things. First is the quantum bit, followed by quantum gates, followed by measurement, those meter things drawn there, that's kind of a representation of measurement. So these are the three things we will think of, but the one-to-one correspondence is pretty simple, right? So what is a quantum bit? I have been talking about qubits, and a quantum bit is very interesting. It has a property that in classical bits, we say that, okay, it's either 0 or it's 1. A quantum bit can be 0, can be 1. It can be something that is both 0 and 1. Right? So this statement is not mathematically precise when we say that it's both 0 and 1 at the same time, but there is no harm for now in thinking that it's both 0 and 1 at the same time. If anyone wants to be very mathematically precise, it's a different structure, it's a different waveform or whatever you think, that it's not really 0 and 1 at the same time, it's a completely different structure, it's a different quantum structure. But it does contain the information of both 0 and 1 at the same time. So why is this useful? Think of this. Just think of this, that let's say that I have two tasks and I want to make you do both the tasks. And I will say that I'll not toss a coin, I'll take a coin, I'll put it. If it is head, you will have to do task 1. If it is tail, you will have to do task 2. Now, if I want you to do both the tasks, I'll have to put the coin 2 times. First, I'll put it as head, then as tail, or the other way, right? Now, think of this. If I could do something like we saw in Sholay, I could just toss the coin and it will drop on the edge. Now, I can actually come and say that, okay, is this head? Is this tail? Maybe it is both. So, you have to do both of them. I actually came up with this example in US when I was in US, and there were too many people around who were studying laws, and they used to come and tell me, okay, we study law, we don't understand, what do you do? Tell us in some simple language. So I came up with this example, and they were lawyers. So they came back with the answer and said that you are saying that if you put it on the edge, it is both head and tail at the same time. I need to do both the work. I can argue and say it is neither head nor tail, and I am not going to do any of the work. So, but yeah, I am not a lawyer. I never thought of it in that angle. But think of it in that way. But the point is, even if we can put it on the edge like that, is it really going to stay on the edge? No, it will actually drop in this direction or in that direction. That is where this measurement comes. We can have a quantum bit or a qubit which is both 0 and 1 at the same time, but the moment we measure it, it will collapse either to 0 or to 1 with some probability. When we think of quantum mechanics, people come and say that, okay, it's a probabilistic thing and all of those things. It is only the measurement that is probabilistic. I mean, those of you who are from physics, you know that it's just a differential equation. There is nothing probability there. The probability comes in the measurement. So, but yeah, you can think of it that way, that the coin will not really remain on the edge forever. It will drop, and the way, the direction it drops, there is a probability associated with it. So we measure and we get 0 or 1 with some probability. Now, there are other things that we can do. So it's not necessarily that we have these A0 plus B1 kind of thing. We can have different kind of things. So for example, this A and B can be 1 over root 2. And now, depending on that, the probability is say 0.5, 0.5. I can have something else. I can say that A is say 1 over root 3, B is root 2 over 3. Then the probability of 0 is 1/3, probability of 1 is say 2/3. And that is exactly what a quantum algorithm is. Now, what a quantum algorithm is, if I say that I have created a coin on the edge, it doesn't make sense, because if I cannot control which direction it will fall, then if I want to make you do task 1, if I cannot control that it will always fall on head, then it doesn't help, because if it falls on, if it goes down on tails, then you will not do task 1. So a quantum algorithm, if you think, is precisely some steps that you start with a coin on the edge, you try to increase the probability such that it will drop on the head. It shouldn't be 50-50. It should be that, ideally speaking, it should be probability 1 that it drops on head, but that is not always possible, as you guys know from probabilistic algorithms and all. But if we can get a sufficiently high probability that it will drop on head, that is also sufficient. So that's all a quantum computer or a quantum algorithm does. It starts with a coin on the edge. It tries to adjust the probability so that we get our desired outcome with very high success rate. So let's think of this quantum computing. So there is a misconception. Many people come and say that since a quantum state can be in superposition, it can be in 0 and 1 at the same time, which I kind of told you that this is not mathematically correct statement. But there is a misconception that since it is a 0 and 1 at the same time, quantum computer is like a huge parallel computer that tries out all possible things at the same time and gives you the best result. This is not true. This is not at all true. The way quantum computer works is totally different from the way a classical computer works. Let's give an example. Let's say that we want to search for an element. So here, as you can see, that we have these blue things, and all of those are elements. Out of that, I am interested in the red one. So we will just look in each of them, and we want to find out which one is the red one, right? That's a search problem. Now, if there is no structure to this, then the best that you can do is start looking at each one of them and see which one is red, which one is blue. How much time it will take? In the worst case, you have to see all of them, right? The way quantum computer can work, just using some technical terms, we walk through the probability space. So what it means, if you randomly select, okay, I'll not check first, second, third like this. I'll randomly take this one, I'll randomly take this one, that one, and all. Even if you do that, you can show actually mathematically that you cannot do any better. You will end up taking, if there are n things there, you will take order of n time to find it. But see, what we showed here is that if A0 plus B1 is your qubit, then the probability is A square. Modulo, it's A square. So A is not probability. A is, in some sense, square root of the probability, and it's called the probability amplitude. Now, a quantum computer can walk through the probability amplitude space. It has no meaning in classical computer if I say that walk through the probability amplitude space. No, it has no meaning. But a quantum computer can walk through the amplitude space, and it can find the element in order of root n time. This is Grover's algorithm, if any of you have heard. This is precisely Grover's algorithm. And if you see what it does, it will do some very precise task. What it will do is, it will change the phase. It will say that, okay, everyone is standing up. Let's take the red one and make it stand down. And if you repeat this many times, the probability of getting the red one increases. So what I want to actually emphasize here is not to tell you how Grover algorithm works. What I want to emphasize is that a quantum algorithm is not a massively parallel classical system. It's something that is totally different from classical system, because saying that you take an element and invert it has no meaning in classical computer. And it is using what we can call as interference and stuffs. So that's kind of what a quantum computer is doing. Now let's come to what we are doing at IBM. So let's go to what a quantum computer is. So this entire thing in the right, as you can see this cursor, this entire thing is a quantum computer. And the whole part of this is actually trying to take the temperature down and down. And the quantum chip, which is actually quantum, everything here is classical, which is actually quantum, will sit somewhere here. It's just a chip. It sits somewhere here. So what is this entire thing doing? It is trying to take the temperature down and down, because the moment the temperature is high, the quantum systems will start interacting with everyone. It's like if all of us start talking right now, nobody will be able to hear anyone. So that's what quantum systems do. They are very bad students. So everyone talk at the same time and nobody can really hear what is going on. So you want to cool them down. No, cool down. So that's exactly what this entire thing does. And it cools it down to around 14 millikelvin or even less than that, which is colder than the outer space. That's what is been done in a quantum system here. And how we interact with it, we as, say, application researchers or things, we are not experimental physicists. What we do is we write some codes which is in Python, which is in some language called Qiskit. I'll come to that. So we write some codes in Python, and we just write it on our own laptop or computer. And then there is, like, just like in classical system, there is a compiler which breaks it down into something we called as chasm code, just like in assembly language code. Then we get it down into bit strings of zeros and ones. But a quantum computer doesn't understand zeros and ones. It understands some pulses. So these zeros and ones are then broken down or converted into pulse, and then it goes here, these pulses, this system is again cooled down and down, the computation happens here, and we get out some result. And this result is now returned to us in some method, in some way that we understand, actually. So that's how the entire process of a quantum computer works. Now, when we talk of a quantum computer, how can we say how performant the system is? There are a few things. First, if I give you, say, 1 qubit, that's not useful. What can you do with 1 qubit? On the other hand, as I was saying, that quantum systems are noisy. So they start interacting with each other. So if I give you 1,000 qubits, everyone is talking to each other. That is also not useful, because you cannot do any useful work with it. So when we think of performance, it is scale, which is the number of qubits. It is quality, which is how good the qubit is. That is defined by some mathematical term called fidelity. And there is also speed, like we have seen that it goes all these things. So how fast it is. Like a quantum computer is extremely fast, but this is the only portion that is quantum, everything else is classical. So if my everything else is very slow, then also we don't get the benefits of a quantum system. So when we talk of performance, we have this scale, quality, and speed. So let's see what we are doing in terms of scale. So this is our roadmap that we started. And interestingly, so in 2016, I was a master's student in Calcutta University, and some of my seniors were, I just started working on quantum computing. Some of my seniors were doing PhD at that time. And one professor actually came that I still don't agree with the argument of that professor, but anyway, that some professor came and told my senior that, okay, you are doing quantum computation, that's great. But is there a quantum computer? No, there wasn't. And interestingly, the day that he said, within a few months, IBM came up with the first quantum computer, 5-qubit quantum computer, that was in 2016. And then we have actually started improving more and more and more. And today, in 2024, we have, in 2023 end, we have more than 1000 qubit systems. And that's like, that's a power of 2 to the power 1000. That's more than, yeah, if you have seen this book of Nielsen Chuang, that's a Bible of quantum computing. They start with this, that if you have 100 qubits, that is more than the number of atoms there are. The computation power of 100 qubits is 2 to the power 100. That is more than the number of atoms there are in the universe. Then he says that is more than the age of the universe. That is more than the product of these two. So that's how much powerful it is. So we have 1000 qubit quantum computers today, and we are moving towards hopefully 10,000 qubits very soon. But at the same time, when we have this system modularity, this is, the systems are something that the experimental physicists work with. But above that, we have other developments requirement, that how do we create a quantum circuit? So we can do good things with quantum circuit, great. You have a problem of chemistry, a problem of graph theory, a problem of physics that you want to solve. How do you take it down and map it into a quantum circuit? That itself is a very important problem to solve. We have something, I'll come to what is Qiskit. We have something called Qiskit runtime that makes running things very simple. And even above that, we have these modules for studying. We have this machine learning module, natural science, chemistry and all, optimization. And then what we have, this is what we call as middleware. So middleware is that kind of where a user comes from this application portion, and there is this hardware. The middleware makes things very simple. It's like scheduling and all of those things, just like it is done in classical. We need to take into consideration some constraints of quantum. So the reason I'm explaining all of these things is, many times we see that people who are not from physics background, they say that, okay, I mean, quantum, we perhaps don't understand quantum mechanics so much, so this is not for me. This is not true. So yes, I agree that in the system level, we need to be an experimental physicist to do this, but everything above this is for computer scientists, is for mathematicians, even physicists. So everything above this, how do you take a problem and encode it into a form that a quantum computer can understand? This is just an encoding problem. Like we do in machine learning, this is an encoding problem. How do you make the system run faster? How do you remove the noise in the system? How do you mitigate the effect of noise? These are physics, mathematics, even CS type problems. What are the good algorithms? Like, what are the things in machine learning, in healthcare, in chemistry, in combinatorial optimization that are actually useful and that can benefit from quantum computers? These are, again, application problems that everyone can actually come and work on. Yes. No, I don't think so. Yes. So very, very recently, around 3 months back, there was a paper from IBM and Riken in Japan. So Riken has one of the best supercomputers. I think it's the second fastest or something, and IBM's quantum device. They could show that if you put these two things together, hand to hand, do some part in quantum, some part in GPU, you can actually simulate some, you can simulate the ground state energy of molecules that is not doable alone by GPU, alone by quantum processors, definitely not by CPUs. So what we expect right now is this quantum centric supercomputing is the term that we have right now, is that these two should go hand in hand. We don't need to think that quantum will replace supercomputer, but we want to find like where they can go hand in hand together. And one example we have already shown is chemistry. And this is again like a bigger, huge roadmap that we have. So in our roadmap, we have two parts. One is the development roadmap that you guys will see. The other is the innovation roadmap that we prepare for next year for you guys to see again. So in this development roadmap, we have quantum systems are noisy. So we have things like error mitigation. I'll touch upon what that is. But if there is error, ideally we want to correct it, not mitigate it. And we hope that by this 2029 and on, or even as quick as 2026 up to 2029, we will have error corrected quantum computers. And the moment we have error corrected quantum computers, obviously we still need to scale things up. There are many promises. For example, perhaps you guys know of this very famous Shor algorithm that says that you can do integer factorization in polynomial time. And if you can do integer factorization in polynomial time, then the classical crypto systems like RSA, elliptic curve, they are no longer secure. The algorithm that I was explaining is called Grover's algorithm, and it doesn't need to be like searching. Grover's algorithm is like extremely rich algorithm mathematically in terms of computer science. You can start applying that on NP hard problems. So don't take this statement too mathematically precise, because if there are any complexity researchers, they will get very angry. But since Grover's algorithm can give a square root quadratic speed up, not speaking very mathematically, what it means is it doesn't say that NP hard problems become easy in quantum computers, but it says that the class NP gets an, it doesn't become P. Yeah, it doesn't become P. I mean, there is no, there is no proof that an NP hard can become P. Factorization is NP. There is an algorithm that factorization can be done in polynomial time in quantum computer. But Grover's algorithm can give a quadratic speed up. So what would have taken us order of 2 to the power n times will now take on a quantum computer order of square root 2 to the power n. That itself is a pretty good speed up. It's not proof saying that P is equal to NP in quantum computer. No, there is no such proof. But it's kind of saying that quantum can give a speed up, a quadratic speed up of the NP class using a quantum device. But again, it's not too mathematically precise. So what I was trying to say is that what we can do if we have a quantum computer. And the day I joined, so the first time I was meeting my team, it was just before Christmas. And they came up with this song during the call that all I want for Christmas is you, this 433 qubit quantum computer. What will happen if we get it? I'll run algorithms and simulation in this quantum world, no limitation. I'll be exploring modern computation, statistics, physics, logistics, my creation. So all I want for Christmas is you, 433 qubit Osprey. So this is very like close to my heart, because this was one of my first meetings when I joined IBM, and they started doing these things before Christmas. So we do funs. It's not like we are always being very serious on meetings. Now, when we talk of quality, we need to think of circuit fidelity, and how we decide that. We have two measures. One is called the quantum volume, and the other is called the EPLG. Let's not go too deep into that, error per layered gate, but let's come to this. There are many problems that we want to solve, say a combinatorial optimization problem, a physics problem, that we can think of that there is an observable and I want to get the expectation value of that observable. Say a graph problem, you want to find out what is the cut size of this graph. You can actually model it as a problem such that it can be the expectation value of some matrix that will give you the cut size. For chemistry problems, it's much more obvious. For physics problems, it's much more obvious. So where we are today is here. We are using something called error mitigation. I'll show you in the next 2 slides what that means. We have classical computers who are doing it great in small scale, but the computation complexity increases significantly and makes it impractical. What we hope is that we will very soon, in certain cases, I think we are already starting to go there, that we can go beyond this complexity where quantum can start doing things better than classical, but not up to its entire promise. And soon, hopefully, we will reach this quantum error correction regime where quantum can flourish its whole promise and whole potentials. So here is this very famous quote from Asher Perez, who said that when you start studying quantum computing, they will teach you all these things about Hilbert space and all. It's just a vector space. And we say that a quantum system is a vector in the Hilbert space. And he said, no, forget all of those. So quantum phenomena does not occur in Hilbert space. They occur in laboratory. What it means is all the imperfections of laboratory are there when you start doing experiments. So yesterday I was talking with my manager that, oh, we have these things now. And he was like, yeah, we have these things in theory, but it doesn't work in practice. So yeah, we need to deal with errors. Ideally, we want to go to error correction, but we are still not there yet. We will hopefully be there by 2029. What we have now is something called error mitigation. So what really is error mitigation? Let's think of this. Let's say that you want to, let me give you a very simple example. It's like the first error mitigation protocol that came out is so simple that it's like, it feels unreal. Let's say that you have a quantum circuit like this. If you run this, there will be noise. There will be some noise associated. You cannot do anything about it. Let's say that I am repeating these gates. So these gates are unitary. By definition of quantum mechanics, these gates are unitary. So unitary means you can always have its inverse. So if you take a gate U, add the inverse to it, again add the gate U, essentially we haven't done anything because U inverse is identity. So we are just repeating it 3 times, but functionally they are the same. I could have used the gate once. I am using the gate 3 times to do the same thing. It's inefficient, but functionally it's not doing anything different. Now, what will happen if I use the gate 3 times? There is noise associated with gate, right? So the result will be even worse. If 1 gate has noise, 3 gates will have more noise. So I'll get a worse result. So ideally you would think that, okay, like this is a stupid idea. Why do you want to replace 1 gate with 3 gate? And the paper that had this from IBM, they will say that, okay, you think it's a stupid idea, I'll replace 1 gate with 5 gate now. You will have even more noise. So you'll say that, what are you doing? Like, why are you, we already have noise that we cannot tackle. You are increasing noise. What are you doing? Now what they will say, think of it. When you are putting the gate 1 time, you have some result, which is not perfect. When you have 3 times, you have a worse result. When you do 5 times, you have an even worse result. You have some statistical data. Now do an extrapolation and try to find out what will happen if there were no noise. This method is called zero noise extrapolation. One of the methods to do error mitigation. So what it says is that I cannot remove the error from the system, but you can do a bit more. You can pay a bit more cost. You have to run a few more circuits. But by running a few more circuits with some classical post-processing, I can give you an estimate of what it would have looked like if there were no error. So that's what error mitigation is all about. And we have this error mitigations in what we call as Qiskit runtime. I'll again come to what Qiskit runtime is, but Qiskit runtime is kind of the interface that we use to deal with quantum computers. There we have resilience level. You can start setting higher resilience level and it will give you better and better error mitigation. Obviously, better the error mitigation, higher is the cost we have to pay. So it's like a trade-off, whether you want to pay more cost or get better results, or you want to pay less cost and get worse results. What we were able to show in 2023, this was a Nature paper, and it was shown in the cover of this Nature, that you can take a 120 plus qubit circuit, a depth of more than 3000 gates, use this error mitigation techniques. They were doing, those of you who are from physics, they were doing something called 2D transverse field Ising model simulation. Those of you who are from computer science, think of it like a graph problem where we are trying to maybe color the edges, color the vertices. So they were able to show that 127 qubit system, this is way beyond anything that a classical brute force system can do. If you are using this type of laptop, what a classical system can do is up to 32. If you are using the best GPUs and everything, what they have been able to show is that you can go up to 50 or at most 60 qubits. Here they showed you can do more than 120 qubits, and the results showed that, okay, no brute force classical computation can go reach anywhere near. There were approximation methods that you can do. There are many approximations and heuristics that you can do instead of doing brute force. What we have been able to show in this paper is at this scale, even the approximation methods are struggling. So obviously, I won't, let's get the entire picture. After this paper came out, there were other papers from other different groups who came up with new approximation methods that could get results as good as the quantum computer. But think in a different way. Till now, what we were trying to show is that a quantum computer is as good as a classical computer or even better. That's what we were trying to show. The scenario now is we have results in quantum that classical people are trying to match. It's flipped. And this competition will be there. And this is healthy because this is actually trying to improve both. Now that we have this kind of paper, classical peoples are able to take this as a benchmark and come up with better approximation methods and show it is doable. And the more they show it is doable, the quantum people will try to go beyond where that is also not doable. So that's a healthy competition that we have. And this regime is what we call as utility. And the day, hopefully, when quantum wins perfectly, like there is no more questions, is what we will call as quantum advantage. That now we have something for which a quantum system can do better than any possible classical systems. Now, coming to speed, we have some methods to determine that. Let's not go into that, but let's come to how you can get started and contribute. So we have many, so if you go to IBM Quantum Learning Platform, we have several learning opportunities. You can see all of these. Each of them are free, and each of them are for different levels. If you are just a beginner, you know something, you are already a professional, there is something for each and every one. And you can go and access the IBM Quantum Learning Platform for free. You will get courses that will teach you even the most intricate mathematical details by John Watrous, who was in Waterloo. You will even get how to start using a quantum computer, how to start writing codes, if that is what makes you more interesting. And then we have other things. So for example, we have something called Qiskit Fall Fest. And this year, so Qiskit Fall Fest is something that you all can apply for. This year it's done. Try to apply for next year. This year from or around Kolkata, IIIT Kalyani and IIT Kharagpur has applied. So it is like a workshop that the students arrange and IBM supports. So yeah, so there are so many things there. We have our software development kit. It is, I have been using this term again and again. It is either called Qiskit or called Quiskit. Nobody knows what the correct pronunciation is. So yeah, so some days back, one of them who are in charge of these, they said that they have created the website in such a way that if you go to this term Quiskit or Qiskit, whatever it is, and ask for it to be like spoken, it will sometimes randomly tell you Qiskit, randomly tell you Qiskit. So nobody knows which one is the correct thing. But yeah, so Qiskit is the one that we use, that's kind of the interface for user to deal with quantum computers. And there are many levels to it. These are some core levels, which is called Terra. We have some simulators that if you are doing some small systems, you don't want to directly go on a quantum computer, you want to test out that your algorithm is correct, your code is correct, you can use these simulators. We have these high level systems for different other things, and I have crossed it out for a reason. There are packages for simulating nature if you want to do chemistry problems, machine learning problems, finance problems, optimization problems. There are packages for each of those that you can use, and all these encoding and things that I was talking about, everything that we know till date, you can directly use from these packages. Just import and use. The reason I have crossed it out is IBM is no longer maintaining those things. The third party people are maintaining. So yeah, if you run into some trouble, we will say that we don't maintain it. But but I mean, this is still good, and clients really use it. If you want to get started, the first thing that you can do, create a free account in this quantumcomputing.ibm.com. You can even do it on a mobile. It's a free account. You just need to have an email ID and an internet connection. You can start by doing something called this drag and drop. You can just play around, like what happens when you put different quantum gates, how does the probabilities change? You can just drag and drop and play around with that. Obviously, that is not sufficient for you to do some useful and interesting work. So you can start learning Qiskit. If you know Python, learning Qiskit is very easy. It's just built over Python. And you can start writing your own codes. And we usually first run it on simulators to verify that the code is correct. And then we go to real quantum devices. Now, there are different areas where this is something I was talking about. And anything that actually interests you, you can go ahead and start working. Those of you who are from physics or chemistry, you can look into this kind of things, simulating systems. Computer science, you can go to this type of optimizations, artificial intelligence. There are so many studies going on these things. And if you feel like that, okay, how can I get started? How can I maybe join IBM or any other companies? What are the steps that we want to take next? So let's say a few things here, just to end with that how can you start contributing. Learning is one thing. So this was the roadmap. IBM, I can tell from perspective of IBM is interested in anyone who can contribute in any one of these stacks. Who can contribute in any one of these stacks, IBM is interested. So if you are an experimental physicist, you can contribute maybe in the hardware preparation. If you are someone who can write great codes and things, you can help by developing these middleware stuffs, how to orchestrate things properly, create circuit libraries, create this interaction, help in writing Qiskit codes. If you are someone who are interested in applications more, how do I develop algorithms? How do I develop like better use cases? How do I find out which problem is better suited for quantum? We have these algorithm developers. And so each and every stack IBM is interested in. Obviously, although I say this mainly for theoretical people, but I guess it's not too important. Still, just for the sake of completion, you can understand that IBM will be interested that you can do algorithms, you can show that, okay, this is order of this and those, they are great. At the end of the day, you should be able to write down some codes and show a prototype. So that will be not only IBM, any R&D lab will be interested in that. But otherwise, research is extremely encouraged here in IBM. If you think of India-specific opportunities, like you can always go to careers.ibm.com and you can see the openings that we have, apply for anything. But if you think of India-specific opportunities, here in our team, we work on error mitigation, machine learning, applications of that, which are the directions where we can apply machine learning. Even I should update this. Now we are also working on biochemistry like protein folding and all with IIT Madras. Quantum chemistry is naturally with IIT Madras, here with TCG Crest and others. And we are also a bit into theoretical studies of what a quantum channel is, how we characterize that, how we do better error corrections and all. We are collaborating with many institutes. Like I am from ISI. I am kind of the first student who started working on quantum in India with IBM, and I am their first hire also. But yeah, in every year, so we have now collaborations with many IITs, Kharagpur, Madras, Jodhpur, Delhi, ISERS, BITS, Pilani, many others. Every year we offer some summer internship, and the call will be around October, November. So if you are interested, look out. It's a long process, unfortunately. For October, November, it's for next year's summer, so 2025 summer. It's paid internship. Look out for it. And internships are a great way to actually showcase your skill. And IBM usually tries to retain good interns by giving them job offers. We have interns who have joined. I was an intern at Watson Lab, and I got joined like that. There are other people in our team also who were interns previously, and they got job offers. So we do that. Now, what if you say, obviously you can understand that internship is quite competitive. So many people are doing. So what if you feel that you are not ready by October or November? You missed out the deadline, but you still want to do some work. So we have this thing that is called global remote mentorship. Whenever in the year you feel like that you have a problem that you want to work on, or even the other way, we feel like we have a problem, we need a student to help us with, we usually advertise in LinkedIn or somewhere, and anyone can apply for there, anyone from Indian Institute. And this is called global remote mentorship. It is not paid, it is unpaid, and you are not required to relocate. You can just stay here. You can relocate if you want, but IBM will not make you relocate because IBM doesn't pay for that. So you can just stay where you want, and you can start working online with anyone from the team who has things for that. We also work on bachelor or master thesis supervision, but that's case by case. So if you really want to do some bachelor thesis or master thesis with IBM, reach out to anyone from our team who you feel is interested. This is still not there. There are plans to start a long-term internships that span 1 semester, but this is still not started. Just one thing to say here, everything I said was in terms of IBM. Let's say one thing in terms of ISI. Those of you who are interested to get started, ISI has some very nice courses on quantum computing, and many of your seniors have been at ISI. Premanshu, Vishal, I was TA at that time. Actually, when they were there, I was the TA. ISI has this joint course with IBM. IBM usually does the practical portions, and the faculties from ISI does the theoretical portion. Some theories are also taken by IBM. So any one of you who are interested, you can always opt for that, and that is actually credited for you all. So yeah, I think that's all I wanted to say. And questions, comments, anything that you have. Yes.
Sir, one question. As we saw in that slide, that for a quantum computer to work, it needs to be cooler than outer space. So energy.
No, not in outer space. It's cooled down such that the temperature is like lower than outer space.
Yes, the
Yeah.
temperature should be very less. So energy requirement is one issue, because in classical systems, we have things which can give very high performance on very low power consumption. So in that curve, as we are at the very bottom, we want to go up. So in the current situation, will the energy requirement also go up, or can we keep the energy requirement somewhat constant and get the performance up?
Yes, so there are actually attempts in this direction. to keep the energy consumption as it is now or even lower it down, but still make it work. So yes, this is actually a valid concern, and there are some funny things that we can say from that. Quantum computer, when it does computation, it doesn't dissipate any heat. You can prove it. Like any reversible computation, there is no heat dissipation. So when people come and say in quantum computer there will be no heat dissipation, the other people come and say, but you are doing so much heat dissipation just to get the temperature down. But yes, this is a valid concern, and what I heard from our not CEO, our director VP here, is that they are thinking of this very important as an important part, that we want to keep the energy consumption similar or even go down, but still be able to do things. Hopefully we will have that.
It is possible to keep the energy consumption constant.
Seems like. I mean, I really don't understand all the experimental physics part, and to be honest, even though I belong to IBM, they are very secretive about it, what they are doing. But it's doable, it seems.
There's no such physical limit that we cannot.
No, there doesn't seem to be any physical limit that you cannot go beyond this with this temperature or this energy consumption. That is not there, at least not known of till now.
Okay, thank you, sir.
Hello, sir. So classical computing is Turing complete, right? And so does the quantum computing. So my question is, how quantum computing can be powerful than the classical computers? In which sense or in which parameters?
Sorry, can you repeat? Classical Turing machine and then?
The classical computers are Turing complete, right?
Yeah.
And I have read that quantum computers are also Turing complete. So in which sense or which parameters the quantum computers will be more powerful than the classical computers?
Yeah, this is an interesting question. So if you see the algorithms nowadays that theoretically show that they are more powerful than classical systems, as I was saying, that the approach is slightly different. They make use of interference properly. So they will say that it's an interference pattern, and you want to interfere them in such a way that your required result is constructively interfered, everything else is destructively interfered. And turns out if you approach it in this way, there are problems which you can do this construction and destruction faster than the time classical would have taken in the route classical is doing. So there are these things, and if you think of what I was talking of Grover, it can go in something called amplitude space, whereas classical probabilistic system will go in probability space, and amplitude space is square root. So intuitively there is a speed up there. So okay, yeah, that's kind of true, is that there are things that classical systems encode in bits. Quantum systems can encode in bits as well as phase. This extra power of utilizing phase is what kind of gives quantum this advantage in certain cases.
Okay, so it's like it's the quantum mechanics which gives us.
It's totally the quantum mechanics that gives the advantage. Yes.
It's two computing paradigms that.
It's totally two computing paradigm. Like these zeros and ones that we have, they are just to make it like the same language of computers. These are not bits in that sense. These are like these electron spins. These can be polarization. So these are totally quantum things. They are just represented as 0 and 1 just to make the language similar to classical.
Okay, got it. Thank you, sir.
Sure.
Just one short question about that. Whenever you're talking about that noise mitigation, right? So isn't it a kind of bootstrap estimation that you are trying to estimate the noise?
Sorry,
is it a kind of bootstrap estimation of noise?
It's in some sense true, some sense not. The example that I gave is a kind of bootstrapping kind of example where we are running it multiple times, but we are not running the same circuit multiple times. We are increasing the depth of the circuit so that the result gets worse and worse. And now we are trying to do a statistical extrapolation on that. There are other methods. There is this method called probabilistic error cancellation. That is a theoretically tremendously powerful method, and the way it works is that you can kind of eliminate the noise entirely by doing proper sampling, but the variance is high. Like there are costs. I mean, if PEC didn't have that variance, we could have said that PEC can replace error correction. But yes, like not all error mitigations are that bootstrapping kind. There are different kinds, and PEC is in fact theoretically more powerful than what I explained, ZNE, but ZNE is more practical because of its low cost approach than PEC.
Thank you.
Thank you.